Match problem 2 gives us a variety of indefinite integral problems to work out, each of these requiring some use of those basic properties we've established so far. In part A, we have the integral of 2 dx. So what's a little bit different about this first problem is that there is no x here. All we have is a constant. So since that is a constant multiple, we could rewrite this as 2 times the integral of dx, but we still have this kind of missing piece of information here. So what we could do is represent this as, or we could insert here, x to the 0. Anything raised to the 0 power is just 1. If we move that 2 back inside, we would just have the integral of 2 times 1 dx. So anytime there's no variable present, we can always think of having an x to the 0 power, which means to integrate this, we would take 2 times x, and then we'd increase our exponent by 1, divide by that exact same amount, and then add that constant plus c, or just 2x plus c in this case. So this is another property that wasn't explicitly stated, but it's a good one to keep in mind. The integral of any constant, well, let's use a k just so we're not doubling up on those constants. The integral of any constant is always going to be kx plus some constant c. So whatever that constant is just ends up being that constant times x. Because if we took the derivative of, say, 2 times x, that would get us back to 2. In part B, we have the integral of 16 e to the t dt. So even though we're using t's instead of x's, this variable matches up with this dt portion. So we're taking the integral with respect to t. We could rewrite this if we wanted to by bringing that constant multiple out front to recognize that all we're doing is finding the indefinite integral of e to the t. We don't need to rewrite this intermediate step each time. That's up to you if that just helps you see that a little more clearly. So now we have 16 times the integral of e to the t is just e to the t plus some constant c. In part C, we're going to have a similar problem. This time though, instead of bringing that 3 out front, I'm just going to integrate this directly. I'm going to skip that intermediate step. So this will be 3 times x to the 5th, since we're increasing that exponent by 1, and dividing by that exact same value, plus some constant c. So multiplying this together to simplify that a little bit, we get 3x to the 5th over 5 plus c. In part D now we have a function that is the sum and difference of multiple functions itself. So what we could do is start off by rewriting this as the integral of 2x to the 5th dx minus the integral of 3x squared dx plus the integral of 1 dx. Again, 2, 3, and 1 are just constant multiples, so we really just need to look at integrating the power function in this case. So this will be 2 times the integral, 2 times x to the 6th over 6. This will become minus 3x cubed over 3. And we have the integral of a constant. So that integral is just going to be that constant times x, so the integral of 1 is just x, and then plus that constant c. So simplifying, we'll get x cubed over 3 minus x cubed plus x plus some constant c. In our last example, we have the integral of, again, the difference of two different terms here. In this case, I am going to go ahead and pull out these constants just since this is an example we haven't looked at just yet. So we could rewrite this as 5 times the integral of 1 over x dx minus 4 times the integral of e to the x dx. So again, pulling these constant factors out in front of the integral isn't a step that you have to take, but it may help to identify what that function is that we're integrating. So in this case, we're integrating 1 over x. So that's going to be 5 times natural log of absolute value of x minus 4 times the integral of e to the x is e to the x plus c.